Almost forgot to unmute. Well, welcome back, folks. Looks like it'll be a small class, but I'm assuming people are getting some good work looking into the recordings. Appreciate you two making it in today. If you have any questions, don't hesitate to stop me at any time. I have a good amount of announcements. We've made it through the third exam. I have the solutions posted here. And also the bigger announcement is we're really on the last two sections of the entire semester. So that means we're likely going to start reviewing for the final exam a little bit early. We're going to spend all of next week reviewing for the final exam. And depending on where we end up, at the end of class on Thursday, we might start reviewing for the final exam. So this gives us enough time, a lot of extra time to get prepared for the upcoming final. Any questions at the moment to start us out today? Okay, well, if we scroll through the last parts of Canvas, we're running out of real estate here. Next week is going to be an entire review week. And for finals week, I have the final exam information published here. I've mentioned in an announcement and that the final exam has to be taken on either Monday, December 15th after 2 p.m. That's kind of a random time set by the math department, or any time on Tuesday, December 16th. I sent out instructions as well, just like the original exams 1, 2, and 3 for scheduling your exam. Forgot to actually mention the date, Monday, December 15th or December 16th, when I said schedule your exam as soon as possible. I just meant scheduling it with the testing center sometime on finals week itself. I'll probably send out a couple more reminders as well, particularly next week going into finals. But as far as the final exam review material goes, I have two versions posted here, just like on the other exams. And there's also a final exam version that's posted on the Newton homework system as well. I'll be posting more materials as well down here and as well on this week when we're doing the review for the final. So pretty much our goal for the rest of the class is finish up these last two sections, these last few topics, and then just turn over to reviewing for the final. Well, that's it for the announcements. Welcome back from the break, folks. It took me a moment to remember where we even were. It was kind of a long break. Well, any questions at all before we jump in? Okay, let's get started then. So section 9.8, solving quadratic inequalities, is kind of similar to what we were doing, say, all the way back here, chapter 7, solving rational inequalities. So we'll tie in how this strategy works with the new strategies as well in our current section as we get through the notes. So first, here's the definition. For a quadratic inequality, we just mean there's a quadratic function somewhere. That's the power x squared. A cannot be 0, so that's still quadratic. And making it inequality just means there's no equals to any longer. Either the less than or greater than, or less than or equals, or greater than or equals. And there's lots of great strategies for solving these kinds of things. We're going to look into the graphical way of solving this, which is a great plan just for the sake of, it's kind of a review topic. If you can graph the quadratic function, then you can also solve the inequality. So we kind of do two birds with one stone. But just for the sake of other strategies, a different way to look into this, we can also solve these purely algebraically without citing a graph. And that's what we're going to do on the second batch, starting in example 2. But first, inequalities are a tricky topic. We spend a lot of time on them when we were in chapter 1, dealing with absolute value inequalities, which have their own set of rules and things to worry about. Then the rational inequalities were tricky on their own. So let's do a review topic, just seeing how those connect with the new kind of problems. So let's call this, say, a warm-up/review. We'll say solve this inequality. Motivated by what we see here, let's suppose it wasn't a quadratic function, but rational. What makes it rational is we're throwing in a fraction now. It's 2x minus 4, divide by x plus 5. Let's say, how about less than or equal to 0, just for a little bit of variety, instead of the greater than 0. So when we went to solve this, the very first thing we went for was cut points. When it came down to a rational function, the way we got the cut points was we took both the numerator, set it to 0, and the denominator, set that to 0, and solve both. Pretty fast to solve these. On this one, we have 2x equals 4, so x is 2. On the second equation, x is -5. So the cut points are 2 and -5. So that's our step 1, just find the cut points. For the next step 2, well, maybe not quite that step 2. For the next step 2, let's put it over here. We used test points to determine the sign of the entire rational function, the thing on the left-hand side, on either side of these various cut points. Well, really, we kind of do step 2 and step 3 at the same time. So let's write out what step 3 looks like. The number line itself. We cut it up according to the cut points we found. So -5 is here. +2 is here. And now we just test 3 different regions for the sign, whether it's positive or negative, in those 3 different regions after cutting up the number line twice. So test points could be, say, something to the left of -5, maybe a -6. So if we pick x equals -6, we threw that back into the rational function. This turns into 2 times -6 minus 4 over -6 plus 5. So that gave us a -12 minus 4 for a -16. Divide by a -1 for a +16. And so it's positive in that region. Then we noticed a pattern when we did this in the class before. We expect the signs to now alternate, negative, positive, unless there's a parentheses around x plus 5 to some even power, like power 2, power 4. That would throw off this pattern. So the only way to be really sure is to just double check a couple more regions. Between -5 and 2, a test point could be x is 0. Plugging 0 up here, we would get -4/5, which is negative. So that sign of negative makes sense. And if we pick another one, say x is 3, then plug 3 up here, we'll get 2 times 3 minus 4. Divide by 3 plus 5. But that's just a 6 minus 4 in the numerator for a +2. Divide by 8. And it's back to positive. So the positive sign here matches with the positive here. And now the last step 4 is to write down our answer in interval notation. First, it's a good idea to fill out what the graph looks like. We go back to the cut points. 2 and -5, they're not both the same. One's an excluded value. The one that makes the denominator 0, the -5. So put an open circle there. 2 is not an excluded value. If you plug in 2 here, you just get 4 minus 4, which equals 0, satisfying the less than or equal to 0 inequality. So we can put a solid dot here to convey 2 is part of the solution set. And now when it says less than or equal to 0, that means we wanted the solutions in the negative region. So if we shade from here to here between -5 and 2, that's our solution set. In interval notation, it goes -5 up to 2 with a parenthesis and a bracket to convey the open circle for the excluded value, and the solid dot 2 for 2 because 2 is a solution. So that's what we did before if we had a rational function. It's a lot of work, actually, writing down all the cut points, doing a lot of arithmetic over here for test points, and then putting it all together. So with that warm-up and review problem, we'll see now how the quadratic inequalities go. So imagine the denominator just moved up here, and this is the similar but different strategy we're going to look into. Well, any questions first with the review problem? Okay, so solving this graphically just means we need some kind of graph that's going to give us enough information to just solve this inequality instantly in one shot. Let's hide part B here. And maybe the best way to get a pretty rough graph, we don't need to find the exact vertex or anything like that, but what we do need is cut points. In this situation, when it's a quadratic equation like this, the cut points are just the x-intercepts each and every time. So just to convey that connection, let's say for cut points, we want the x-intercepts. And finding the x-intercepts on this is not too bad. You take the rational function, 2x minus 4 times x plus 5, and just set that whole thing equal to 0. That would give us the x-intercepts to this function here. But this is already in a factored form, so getting those x-intercepts is fast. We just take, feels like deja vu, each side or each factor, set it to 0 and solve. So 2x minus 4 equals 0, or x plus 5 equals 0, gives us x-intercepts, x equals 2 and negative 5. If we wrote them out as coordinates, it would be 2, 0, negative 5, 0. So we're ready to start drawing the graph, which makes sense. We're doing this graphically. I don't have a lot of information on the graph just yet, but intercepts is a good start. We have one intercept here at 2. This solid dot here is not meant to be the same kind of solid dot we put on just an ordinary number line. I'm just putting down the dot just to convey that's a point the graph is going through. So less like the solid dot from before. Then left 5. So the graph goes through here. But now it gets a little bit tricky because there's two possibilities. Either the parabola looks like this, which will give us one particular set of solutions, or the parabola looks like this, which gives us a totally different set of solutions. In other words, we have to determine if this opens upwards or downwards, but there's a pretty easy fix for this. In fact, we can see from visual inspection alone, when you look at that, if you were to FOIL this all out, the leading coefficient would have a positive value, so it would be opening upwards. But let's see the details on paper just to connect all those thoughts. So we'll write, here's our quadratic function we're dealing with, y equals 2x minus 4 times x plus 5. It's in a factored form, which was helpful for the x-intercepts, but if you're wanting to see it in standard form, you would just FOIL this out, distribute 2x. We get 2x squared plus 10x. Distribute the negative 4, and we get to negative 4x minus 20. My zeros have a habit of looking like the number 6. Let me fix that. So now simplified down, we have 2x squared plus 6x minus 20. But because the leading coefficient is a positive 2, 2 is greater than 0, we can say that this opens upwards. And that's good news for us. That means when we go to plot this whole thing, here's what it would look like. And again, it's a pretty crude plot. I don't know exactly where the y-intercept is. I don't know exactly where the x-intercept is. But for the purpose of just solving an inequality, this does the job. What we look into next is greater than 0 is telling us where our solutions should be. This means we want the positive regions. So just like here, less than or equal to 0 meant our solution set was the negative region. Here we'll take out positive regions. And we can actually pretty much write down that solution set immediately. But just as the sake of visualizing this even further, let's put down a number line below. That number line had a cut point here, right at negative 5. Another cut point here, right at positive 2. And here's how you can tell where the positive and negative regions are. It's just completely up to that graph now. Once I get these curly braces in, there we go. Wherever the graph is above the x-axis, the whole thing on the right, 2x minus 4 times x plus 5, or in the standard form, 2x squared plus 6x minus 20, wherever the graph is above the x-axis, that parabola or quadratic function is positive. It goes to 0 at negative 5, but when we're between negative 5 and 2, we're now on the negative end. If we go beyond 2, the whole thing, 2x minus 4 times x plus 5, is positive. And so we just put a plus to convey above the x-axis. Wanting the negative regions tells us we're in this region between negative 5 and 2. This is strictly greater than 0, so we put an open circle on both. And now the solution set is all real numbers between negative 5 and 2. So in interval notation, it's negative 5, positive 2 is our solution set. So once we got those x-intercepts, it told us exactly where the solutions lie, and the whole problem is over. In my opinion, the warm-up problem took a little bit more work. We had to be really careful with all the test points. But for this problem, once you see the x-intercepts, which was really fast, 2, negative 5, and once you observe that when you FOIL this out, you get a 2x squared, same as that 2x squared we got when we FOILed it out fully, we knew it opens upwards. And that's enough to just put down a really fast plot like this. You might not have even FOILed out 2x minus 4 times x plus 5. Just observe you get the positive 2x squared to get that graph instantly. So these are the new problems. The strategies feel quite a bit different, but there's a lot of similarities still. There's still a notion of cut points. We're still ultimately organizing the information on an x-axis and then back down to interval notation. The new thing is the graph itself is guiding us on where the solution set is going to be. Well, any questions on the first problem? Okay, let's try out how different these can get. With the same instructions, we want the solution set in interval notation to x squared minus 5x. And when you look at that thing, sometimes we have to resist a particular urge in algebra of doing something like this. So let's call this a warning or maybe caution. In solving the one below, negative x squared less than or equals to 5x, we cannot divide by x. And it's tempting. If we did divide by x, we would have an ordinary inequality, the same kind of stuff we solved back in chapter 1, and that would seem like it's faster to solve. But the reason we cannot divide by x is we know that when we multiply or divide both sides of this inequality by a negative number, this direction of the inequality will switch on this. Also, x could potentially be 0 as a solution to this whole thing. If we divide by x, we've divided by 0 as well. And so there's a couple problems. So we do not know if x is positive, which if x is positive, we could divide by it. It won't flip the direction. But we also don't know if x is negative. It's a variable. It can take on any real number. But if x is negative and we divide by it, there's now two sets of inequalities you have to solve. When it's less than or equal to, or when it's greater than or equal to, when the direction flips. And also, it gets worse. We do not know if it's x is positive, negative, or 0. And when you divide by 0, we're losing all the information. We just get undefined. But 0 could be part of what we need in this solution set. So we have to resist our urge on this one right here, not divide by x. Instead, we want to get it into this form. we need to get 0 on one side, and then all the steps that we took in part A would go along with part B as well. So that's our quick caution. The way to solve this is, let's say, how about we subtract 5x from both sides? You could add x squared to both sides if you prefer. If we subtract 5x, we'll have negative x squared minus 5x is less than or equal to 0. The next thing that made the prior problem a lot nicer was, I can scroll to the right spot, it was in a nice factored form from the very get-go. So that's the next thing we want. We want this thing factored as well. It doesn't factor as a pair of binomials like what we have above, but we still can pull out the greatest common factor, either factor out a positive x or a negative x. Let's go with factoring out a negative x on this one. Factoring out negative x leaves us with negative x times x plus 5 is less than or equal to 0. Now at this stage, we can proceed as normal, solving this thing. First, the polynomial function, or the quadratic function, y equals negative x squared minus 5x in that form, does tell us some good information. The leading coefficient is a equals -1, which is certainly negative, less than 0. So it tells us that the graph of this parabola opens downward, as opposed to what we saw here with a positive 2 for 2x squared. We had it that it opens upwards. So we're opening down on this. Next thing we need are cut points, or we can just say briefly on this, x-intercepts, which are the cut points. Finding the x-intercepts is fast. We just set both of these factors to 0. So we have negative x is 0, or x plus 5 is 0, but that just immediately implies x is equal to, say, divide both sides of this by -1. You get 0, subtract 5 on this, and we get -5. So as actual ordered pairs, the x-intercepts are 0, 0 for the origin, and -5, 0. Now we have everything we need to get started. We'll put down a rough graph. Observe that we want the negative regions for the direction of this inequality, and just state the interval notation. Well, here's the quick graph. One intercept here at 0, so one cut point, then left 5. Here's the other cut point. Opening downwards means the graph looks roughly something like this. Not my best work for a quadratic, but let's let this one stand. It doesn't have to be perfect, but it does convey all the information we would want out of this. Let's hide that one down below. For the less than or equal to 0 part, this tells us the regions we want. We want negative regions. So down below, here's the number line associated with the graph above. One cut point's at -5, the other is right at 0. Which means ordinarily that's 3 different regions to test. But if you have our graph ready to go, you don't have to do any of that testing. Just look where the graph is. To the left of -5, it's below the x-axis, so this whole region is negative. But if you move to the right of -5, you get positive values out. So plug any value of x, say -3, inside here, and this whole thing comes out as positive. So this entire region goes positive here. But once you go to the right of 0, it flips back to negative. And those are the regions we want, all those negative regions. So with this graph arranged in this way, it's a less than or equal to 0, so we'll have a solid dot here, another solid dot here, so -5 and 0 are solutions. But we shade in the direction of the negative regions that we needed. for the less than or equal to 0 inequality. And as a graph, it's pretty much this we're staring at right here. In interval notation, the solution set becomes negative infinity up to -5 with a bracket, and then union, another bracket, 0 off to infinity. Blue to just convey those numbers came from the original x-intercepts or cut points. So if you can imagine, if we did start off this problem by, in fact, dividing by x on this, or dividing by -x, either version, there's no way we would have gotten both of these intervals. We might have gotten one, and by luck, it might have been correct, but that would have just been sheer luck alone. We wouldn't have gotten the full set like we got here. So quadratic inequalities are kind of nice because you've got options. You can do this purely algebraic, like we did on the warm-up problem of the day, or you can just fall back on the graphing techniques, which we are slightly reviewing on these problems, and use it to just power through the interval or the number line and then down into the interval notation. We'll try this out one more time and then see how to do it algebraically in the next problems. Any questions or comments at the moment? Okay, here's the next version. I feel like these all deserve a clean page, so let's push this down. So x squared plus 13x plus 40 less than 0. It's a nice problem in a certain sense. We have 0 on one side, so we don't have to rearrange it. And if we write out that the quadratic is y equals x squared plus 13x plus 40, the leading coefficient here automatically reveals itself to be a positive one. So it tells us that this parabola is going to open upward. So that gets us started, but for the next thing, the cut points, this would be more convenient if it was in a factored form. So let's let that be our next step. Let's actually factor this down. So x squared splits as x and x. If factoring looks tricky, we might have to fall back on the quadratic formula. But good factors for 40 are 8 and 5. 8 and 5 add up to 13. So it looks like we don't need the quadratic formula on this one. So go plus 8 plus 5. And now with its factored form, the cut points, or you could call it x-intercepts, are just immediately revealed. The x-intercepts, let's call it that way, are, well, if you plug in a -8 here, you get 0, so that's one x-intercept at coordinates -8, 0. If you plug in a -5 here, you get the next intercept, so -5, 0 as well. And this is enough information to get, again, it's a crude graph, but it's everything we need to solve the inequality. So that's our next step now. So as we do that graph, the less than 0 part, just as another reminder, tells us we want positive regions. But that will just be the regions where the graph is above the x-axis. So here's the graph next. So 1, 2, 3, 4, 5. Here's our first intercept at -5. Our next intercept is at -6, -7, -8. Down below, we'll reuse that information on a number line at -8, -5. And in one shot, get the signs for all three regions. Last thing is the graph. It has to go through these 2 points for sure. But because it's opening upwards, we cannot draw a graph that looks like that. That's an opening downwards graph. Instead, our graph looks like this. Let me try one more time. I don't know the specifics of where the vertex are or where the y-intercept might be. Well, we do know the y-intercept is at 40. If we plug in 0 for x, we get 40, so it's way up there. But this is the minimal information we need to fill out the sign chart. Left of -8, it's positive. Between -8 and -5, it's below the x-axis, so we're negative here. And to the right of -5, we're above the x-axis, so positive in this region. And I think I made a mistake when I wrote this out. Must have been a long break. Less than 0 is not as saying we want positive regions. Let's correct that here. Less than 0 means we want negative regions. So let's double check. Yes, we want negative regions here. When you make a silly mistake like that, it doesn't hurt to double check what you did everywhere else. Bigger than 0 means positive values, so positive regions here. So watch out for silly mistakes like that. It's kind of rough to make everything right, but just had a brain fog on that one critical detail. So now that we know we want the negative regions, the number line is going to look like this. Open circle at -8 and -5 because the strictly less than 0. Shade in between. And as a graph, that's the entire solution set on the number line. In interval notation, it's -8, -5. I know -5 came up a few times. That's kind of weird deja vu there. The next numbers are going to be a little bit different though. Well, we did it, folks. This is solving these kind of quadratic inequalities so far in a nutshell. And if you like this kind of technique, this is kind of great because this works really in all problems. We're going to look at a different method just to give some variety on how to solve this. You don't always have to draw a graph. And so that's what the next example is all about. But if you feel like this is a great approach, this could do the job for filling out the homework essentially. Any last questions at all before we go to the next examples? Okay, so for the next, we're going to switch gears. The graphs are still important, but we're not going to draw them on paper. We might refer to them using the Desmos calculator just to get some deeper insights on what happened on the paper, on the notes. So example 2 now says, solve inequalities algebraically as opposed to graphically. Same goal for the solution set. We'll write out an interval notation. And I'll continue to use the number line, the graph as well, just as a guide to getting that interval notation accurately. First problem on this that we observe is we don't have 0 on one side, so let's start off by subtracting 1 from both sides. The new inequality is x squared plus 3x minus 1 is less than 0. So the quadratic function that we're analyzing is y equals x squared plus 3x minus 1. It opens upwards. Leading coefficient is a bona fide 1. So it opens upwards on this one. Now, next thing we want, just like before, are the cut points. But you know, that's a little bit trickier this time. There's no great way for me to factor this using integers like I have been able to do on the last problem, like the negative or the +5, +8 on the last one. A 1 here just doesn't give me a lot of leverage, and we're trying to come up to a 3. So this turns into a big review problem. We need the quadratic formula this time to get our x-intercepts, or so-called cut points. So for the x-intercepts, we're taking x squared plus 3x minus 1, setting it equal to 0 and solving. Quadratic formula tells us the solution to that is going to be x equals -b plus or minus the square root of b squared minus 4a times c divided by 2 times a. So now putting in the information here, let's say what the coefficients are and work out the discriminant. A is 1, like we said above. B is 3, and C is the constant term, -1, coming from that quadratic function. So the discriminant, b squared, minus 4ac will turn into 3 squared minus 4 times a, which is 1, times c, which is -1, so plugging in the values there. This gives us 9 plus 4 for 13 altogether. That's the problem why this was hard to solve. If that was like a 4, or maybe a 25, or 81, you'd put all those perfect squares inside here, and then the square root is going to give you a nice integer. And that's why if the discriminant is a perfect square, this actually could have factored in a nice way. But with a prime number like 13, we don't have nice cut points or nice x-intercepts. We're going to have to write them out like this. X equals negative b gives us a -3 here, plus or minus the discriminant, which we worked out to a 13, divide by 2 times 1, so just a 2. So that's what the x-intercepts look like as actual coordinates on the plane. These would be -3 minus root 13 divided by 2, comma 0, and -3 plus root 13 divided by 2, comma 0. So that's, again, kind of inconvenient, but we can work our way through that. Sometimes the numbers are just not convenient. They can come up in the homework as well. When this happens, next thing to do is just place them on the number line like you have been doing before. Doesn't matter how complicated the numbers look, they just have to be real numbers to place on the real number line. So this is the smaller one because it involves negative root 13. So here is -3 minus root 13 halves. It's going to be valuable to get a number for that, so let's compute it. -3 minus square root 13 divided by 2, it's about -3.3. The other cut point, or x-intercept, is at -3 plus root 13 divided by 2. So let's flip that inner sign to plus. And it comes out to 0.3, so positive on this end. And now we're ready to start testing regions. So we have a region here, here, and here we'd like to test out. We never drew the graph because we're solving it algebraically. But if you thought about this right here, you're probably pretty much done testing the regions. If it opens upwards, that means the graph is going to look essentially like this. So it should go positive, negative, positive. So if you like that view of doing this kind of problem, you're still thinking about it graphically, but I'd say that's totally fine. That'd be a great way to do it. I don't know if it's 100% in the spirit of the instructions, solving it algebraically. So I'll give you a different approach for the notes. But again, if you like to solve it algebraically, or excuse me, graphically, like we mentioned, I'd say that's totally fine for this problem. Algebraically means we go from the cut points, or the so-called x-intercepts, to the test points. Here's where it was helpful to know the rough numerical value of these regions. If this is -3.3, then the handy number in that region there would be x is -4. We take -4, plug it into the original quadratic, and just see what the sign is. So at -4, we get -4 squared. 3 times -4 minus 1. This is 16 minus 12 minus 1, which is altogether 3. So bigger than 0 for a positive on this region, which means we probably expect negative on this region and positive, but let's continue to test just to be ultra sure. So to the left of 0.3, this x-intercept here is a good test point. X is 0. That one's really convenient. Plugging 0 here gives us 0 plus 0 minus 1. So we just get a -1 immediately, which is negative. And it tells us this sign is right. And finally, a good test point in this region, to the right of 0.3, would be X is +1. That one's not too bad to work with. When X is +1, this just becomes 1 plus 3 minus 1 for a +3 again, which matches up with the positive sign here. So almost done. Feels like a lot more work when you do it purely algebraically and you're not paying attention to the graph. But we're just about there, so that's the good news. With less than 0, this tells us we want the negative regions. So now back on our graph, we'll put open circles around these cut points because of the strictly less than 0. There's only one negative region, so we'll shade in the middle. And that means we've done it, folks. This one is kind of a lot of work because it involved a lot of concepts. Quadratic formula came into play out of nowhere. The solution set in interval notation looks kind of ugly, but it's a quick way to say it. It's -3 minus root 13 halves up to -3 plus root 13 halves. I'll highlight those in blue just like before, just to convey they came from the cut points. And our work is done on that one. Well, this one was kind of, again, a review problem mixed into the concept of the 9.8 notes. Any questions at all getting through this one? Okay, let's try this out a couple more times. So last two questions. These are ones that are slightly weirder that can come up as well. I like the 0 on one side on this one. That gives us a nice setup, a nice start to it. But looking at a 3, x and a 3, this is another one where it doesn't factor too nicely. So first step is to look for cut points on this one, just like before. You can call it, like we mentioned before, cut points or x-intercepts. I'll just go with the generic cut points on this one. To get the cut points, take this part right here, the quadratic function, set it to 0. X squared plus 3x plus 3 equals 0. We observe this looks like a quadratic formula type of problem, so let's write out the formula. X is -b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Well, before we get too far on this one, let's also look into kind of a review topic for something we've seen back in the day. Not too far back in the day, back when we were graphing quadratics. Let's see, I think I want 9.6 version. There's a great topic that ties into this once again. For using the quadratic formula, there was a lot of information about it that's relevant to what we're doing right here. Okay, somewhere here, I believe, is a quadratic formula readout. There it is. We were solving a problem pretty similar to what we're looking at here, x squared plus 2x plus 2. We were going for a high level of detail on the plot, so we wanted the vertex, y-intercept, x-intercepts. But once we plotted the vertex and we observed that it opened upwards, we noticed finding x-intercepts was kind of silly. There are none. If you try to force it, you set 0 equal to x squared plus 2x plus 2, write out the quadratic formula just like we're doing right here on the notes. But if the discriminant comes out as negative, that means there's two complex value solutions to this quadratic 0 equals x squared plus 2x plus 2. But that means there are no x-intercepts whatsoever. So the concept that's relevant back here is the discriminant is also going to tell you about your x-intercepts as well. Cut points, I almost wish I called that x-intercepts. Let's bake that in. Cut points slash x-intercepts. essentially synonymous in this section. If you get a positive discriminant, just like on the last problem we looked into, we get two real number solutions, but that just means two x-intercepts. It's possible to get one real number solution, so one x-intercept. But if this ever comes out, a negative discriminant, that means there are no x-intercepts whatsoever. There's two complex number solutions, but they can't be plotted on the x-axis. So with that in mind, let's see what happens on this one. We have, reading out the ABC coefficients, A is 1, B is 3, and C is 3. So now, paying really close attention to this thing, the discriminant, b squared minus 4ac turns into 3 squared minus 4 times 1 times c, which is 3. Then working this out, we get 9 minus 12, which is a negative 3 less than 0. But that means we're back into that same situation that happened back in 9.6. This tells us right here, for our discriminant, there are two complex valued solutions. And this means no x-intercepts, or no cut points if we set it that way. So up here, we can come back and just say none. Doesn't mean there's no solutions. That just means there is no cut we make on the real number line. Either every single number is a solution or no number whatsoever is a solution to this quadratic inequality. Well, we can still solve this algebraically, purely by doing the same kind of thing. There's no cut points. It looks a little weird, but we just make no cuts. So here's our number line. It means testing the regions goes really fast because there's just one region to test. Between negative infinity and infinity, we just need to pick one single number and we can test this region in one shot. I would argue the easiest number to test is x equals 0. So let's use that as our test value or test number. Set x to 0. That means putting 0 up in here, we get 0 squared plus 3 times 0 plus 3. All that's left is 3, which is bigger than 0. So the entire region tests as positive. It's kind of strange and curious. And if we look into the inequality once again, greater than or equal to 0 told us we want positive regions. But the positive region is the entire real number line. So in interval notation, it tells us the solution to this inequality is all real numbers. It would look like this, from negative infinity to positive infinity, or in words, this is equal to all real numbers. So there's no value you can pick that makes it false. It's always going to be true. X squared plus 3x plus 3 is always positive. Well, any questions at all? Finalizing this one. Okay, this is one where if we did look at the graph, it probably would have been less mysterious. We probably wouldn't have spent maybe any time at all thinking about the quadratic formula. We could have skipped these steps. The graph to this kind of just spills the beans immediately. It tells us everything we need to know, right? Y equals x squared plus 3x plus 3. And here's the result. We might use a vertex formula to find that vertex, but once we notice that this has a positive leading coefficient and it opens upward, we would know that the vertex is the lowest point. So if we're doing this graphically, we might use the vertex formula to determine the whole graph is a parabola opening upwards, never even touches the x-axis. We determined that algebraically. There's no x-intercepts, that's why it doesn't touch the x-axis. But we would have also known through the graph that it's always greater than or equal to 0. So if we want positive values, it's all real numbers whatsoever. So that's just a different view of what's going on in this problem. We'll try out to one more weird one before we take a look into the next set of notes. But any last questions on part B? Okay, so let's see what's going on the next portion, part C. First, it's a little bit scrambled. We don't have 0 on one side. X squared is on another side. So we can fix that pretty quickly just by subtracting 6x and adding 10 to both sides. We'll get 0 is greater than x squared minus 6x plus 10. Now we have our 0 on one side. It seems kind of weird because every inequality we've solved so far in these notes had 0 on the right-hand side. But this is totally fine to just leave it like this if you prefer. If this switch of directions is kind of jarring, you can just flip the whole inequality. We've done that before in the past. If you decide to flip it, write in this side first. X squared minus 6x plus 10. Just make sure the inequality is pointing towards the x squared minus 6x plus 10 side. So it was greater than or equal to 0. Now it's less than 0. That's the same equivalent inequality. So just like before, if we're solving this purely algebraically, we could go and look for the cut points or say the x-intercepts. But another way to think about this is, what is the vertex of this thing? Let's go with the vertex route. So if we have y equals x squared minus 6x plus 10, we know that the leading coefficient is a greater than 1. Excuse me, it's a equals 1, which is greater than 0, I mean to say, which tells us this graph also opens upwards. So if we can find the vertex, and also knowing that it opens upwards, we're still using algebra. Vertex is a other review topic we can take a look into. This will give us a good idea of what the solutions would look like. So let's use next the vertex formula. The vertex is going to give us the coordinates x, y, but the way we get the x coordinate is through this formula. X equals negative b, divide by 2a. The first time we used this vertex formula, we had the reminder that a great way to memorize it is this negative b over 2a portion right here is that vertex part. So if you ignore the plus minus square root of the discriminant, that's just one portion of the quadratic formula. B coefficient in this problem is negative 6, so we will plug in negative of negative 6, divide by 2 times a. A is 1, like we said earlier. So this is just positive 6 divided by 2 for 3. That goes into the first coordinate for v, the vertex. And now to get the second coordinate, y, we just go back up here. Y equals x squared minus 6x plus 10. But we substitute in place of all values x, 3 that we just found. So this will become 3 squared minus 6 times 3 plus 10. So now it's 9 minus 18 plus 10. So that's 19 minus 18 for a positive 1. So the vertex formula tells us the vertex, which is going to be the lowest point on the graph, is at 3, 1. It also opens upwards, so our graph is never going to hit negative values. Yet this less than 0 tells us for the solution set, we want negative regions. But looking at the graph on this, the graph of just the number line, that will never actually occur. If the vertex is at a positive region 3, 1, and the graph opens upwards, without even looking at a test value, we know that this is always positive. There are no cut points, no x-intercepts. And if we did peek a little into the graph of this one, we're thinking graphically, but we did solve it algebraically using this algebra here. The vertex is at 3, 1, so right here, opens upwards, so the graph looks like this. This might be a mental picture in your mental blackboard as you're imagining this information. It tells us it's always positive, like we wrote here on the number line. That's compared with this opening upwards, never actually extending into a negative region below the x-axis. But we wanted the negative regions, so this is like the opposite of the last problem. This time, there is no solution. And so the way we would write this down in interval notation doesn't work any longer. There's no interval of numbers for interval notation, but we can use this symbol here. That's the empty set symbol, or just a way to say no solution whatsoever. So that's the empty set. Well, that does it. That's the scenario for looking into solving quadratic inequalities. Also, this is an exciting point of the course to be in. That was the penultimate section for the entire course. Next section on 11.1, we're looking into the distance formula equation for circles. That will be the last section for the entire course. Distance formula is a nice algebraic tool that'll be useful later on in other courses. It goes back to Pythagorean's theorem, so that's kind of a nice connection. And in equations of circles, those are useful tools as well. Very helpful in trigonometry if you're going to be taking that course. But also it loops back with completing the square as a technique, as we've used elsewhere in the notes. So let's save this up and take a look into what's going on in the next section. Okay, so here it is. The last section of the entire class. That's kind of a nice feeling. Congratulations on making it to this point. We'll finish off this section most likely sometime on Thursday, and then convert over to talking about and reviewing the final exam. But first, here's the distance formula. It says the distance between 2 points, x1, y1, x2, y2, is given by this formula. It's kind of an interesting formula. It's a lot to memorize, but a great way to think about this formula is it should feel almost like deja vu in a certain sense, because we've worked formulas that, sure, they're different, but they have a lot of similarities. So go back all the way to chapter 3, slope of a line. It's been a while. This is like, say, week 3 of the class. So back when there's daylight still, when we were taking this class. But here's the slope formula. M is y2 minus y1, kind of like the y2 minus y1 here, divided by x2 minus x1, the change in the vertical direction, divided by the change in the horizontal direction. But here's x2 minus x1 as well. So if you can use a formula like this just by plugging in information like we did before, it's not too different from using this formula either. Just a different rearrangement of all the variables. Like before, there are 5 different variables. They have different tags to tell x's apart, to tell y's apart, and then a 5th variable for distance, or just like here, the 5th variable for the slope m. But a good way to kind of get a feel for this formula is where it comes from in the very first place. So before we use this formula, we'll just justify why it's true. That can help us memorize it for the purposes of actually using it. Let's draw just a random XY plane and a couple random points. I'll let this point down here be x1, y1. This point here, just for the sake of convenience, looks like everything is in quadrant 1. But these points could be anywhere. They could be on an x-axis. They could overlap on top of each other, then the distance is 0. And they can be in different quadrants. So this will be x2, y2. The distance d would be this line segment here. And finding out the formula for this distance is kind of vague if this is the whole diagram that we're looking into. But we can extend on this diagram. And the nice thing about this diagram is if we drop down a perpendicular and a horizontal line, in this kind of way, we build a right triangle. This diagram is kind of busy already, so let's pop the right triangle out of this display and analyze it as kind of its own thing. So here's that same right triangle from before. It's a little bit easier to visualize with the less noise with coordinates and x and y axes. Here's the distance d that we still want to find between this point and this point. It just so happens to be the hypotenuse. We also need to know the length of this segment going from here to here. The length of that segment, well, it's not quite x2. x2 would be from the distance all the way to the axis here. If you take x2 minus x1, that's this length here, the distance from x1 to the y-axis, that's the entire length going this way. And that's this part of the formula right here. Likewise, we also want to know the height, or this length, the length of that leg. So this leg right here, just like before, it's not quite y2, because y2 is the length from here all the way down to the x-axis. But if we subtract this length, this is the length y1 from this point on down, we get that this length here is just y2 minus y1. And so that's where that value comes into play. So next thing we do is we just use Pythagorean's theorem on this right triangle. And Pythagorean's theorem will tell us that the square of this side, the hypotenuse, so d squared, would be equal to the square of this side. This would be x2 minus x1 squared. And let me fix that subscript. That's x sub 2, not an exponent of 2, minus x sub 1 power 2 plus then y2 minus y1 power 2. That's just taking what we often call c and squaring it over here. What we often might call an a, squaring it over here, and what we would call a b and squaring it down there. So Pythagorean's theorem gives us this altogether. And that's essentially the distance formula. Well, not exactly, that's the distance squared formula. So if you wanted it, what you want is strictly the distance. You just have one more step. Solve for distance by taking the square root. And distance equals square root. We only take the positive version because we have a positive distance. Our distance can't be zero. Excuse me, it cannot be negative. It can be at the minimum 0. So it'll be x2 minus x1 squared plus y2 minus y1 squared. So that's the logic and how the formula comes together. And in a certain sense, it's kind of good news in a way, because if you ever forgot this formula and you have two random points you want to find the distance between, you can just build a right triangle from scratch like this and work it out. All the distance formula really gives you is a slight shortcut, so you don't have to write or draw a right triangle. You don't have to do the middle step at all. You could just jump right into the punchline, square root of the difference between x's and the difference between y's. So that's where the distance formula comes from. On the next problems, we'll just practice out how it goes. I don't want to go too far in the notes since a lot goes on in this section, but let's practice out maybe part A for our next problem, and then we'll call it a day just a little bit earlier today. Well, any last questions on the derivation for the distance formula? Okay, let's practice this once, and then when we come back on Thursday, we'll refresh ourselves on how this goes. We'll see how this connects with equations of circles, which is interesting, and complete the notes. So here's our distance formula. Distance is the square root of the difference in the x values. Let's keep that color coding going. Plus the square of the distance in the y values. So if we want to find the distance between these two random points, you could sketch out the graph, build a right triangle, use Pythagorean's theorem. All of that works just fine, but let's treat ourselves to just Pythagorean's theorem. So here are the x-coordinates. You could label them as x1, x2. Here are the y-coordinates. We could label these as y1, y2. And just like with the slope formula, this is a pretty forgiving formula. It turns out it doesn't matter how you label these. In this problem, if I label this as x2, y2, x1, y1, and use the same formula like this, the numerators are going to be flipped and so are the denominators, but we get the same exact value. And same miraculous thing happens with the distance formula. If you call this x2, y2 and this x1, y1, it actually doesn't matter. You get the same exact values right here. So however you label these points, it's always going to work out. As long as you're subtracting the x-coordinates only and y-coordinates only in these two spots, you'll always get the right answer. So finalizing this problem, distance is going to be equal to square root of, it'll be 1 minus 5 squared. Don't forget the plus in the middle. Then next is negative 6 minus 0 squared. And now it's just an order of operation problem. Distance is the square root of, work inside first. This is going to be a negative 4 squared plus a negative 6 squared. We have to be pretty careful with the exponent laws here. Recall these parentheses are actually critical and important. If you wrote it this way, negative 6 squared, this is mathematically equal to negative 36. But these values are always only positive. What we really need to say is you're taking negative 6 with a parenthesis and squaring it, which is negative 6 times negative 6, giving us the right value, a positive 36. So really, that's probably the biggest main danger about the distance formula, making a slight mistake with the notation of exponents. Keeping those parentheses down and firm helps us be accurate and not make that kind of mistake. So now we have a 16 here plus 6 squared. It's going to give us a 36. And the more you think about this, the more dangerous this problem gets. Because now that we're here, it's tempting to use another mistake. If you take, say, the square root of 16 plus the square root of 36, that'd be 4 plus 6, which is 10. But this is not 10 whatsoever. The square root of 16 plus 36 goes differently. We still have to follow the order of operations completely. Work inside first. The square root symbol is a legitimate grouping symbol, like a parenthesis. 16 plus 36 is going to give us, let's see, add 10 is 46, plus 6 will give us 52. And the square root of 52 is absolutely not 10. So the big warning here, let's use a big color to highlight this, is that square root of 16 plus 36 is not equal to the square root of 16 plus the square root of 36. Unfortunately, if that were true, a lot of algebra would simplify in a massive way. But pluses or minuses mess algebra up in a big way, and this is one of those times it occurs again. The problem is still tricky because now that we have a 52, we still have to reduce our square roots like we would have in, say, the chapter 8 section for roots. So let's work on that next portion. Root 52. Well, we can divide a 2 into there and get 2 times 26 would give us a 52. 2 goes into 26 13 times, and that's a nice thing to see, a prime 13. So 52 can be factored as 2 squared times 13. Coming back over here, the square root of 52 is 2 squared times 13. So taking the square root of this, first, the square root of 2 squared just gives us a 2. We can't do anything with the 13, so it just stays as a root 13. And that's the exact distance between these 2 points in the plane. Not something I would have guessed, 2 root 13. But here's the lay of the land. If we go, say, 1, 1, 2, 3, 4, 5, 6. Here's the first point. 1, 2, 3, 1, 2, 3, 4, 5. Here's the second point. The distance between those 2 points is exactly 2 square root 13. Not some value would have guessed. Certainly not 10 if we simplified it in a strange way like over here with this warning. So even though the distance formula is a pretty fast formula to use, it has a few pitfalls to be careful with. But we did it, folks. This is our first run at the distance formula. We'll practice it again when we come back on Thursday's class. And we'll then also see how the distance formula connects with equations of circles. Any last questions at all before we call it a night? Okay, well, have a good one. I'll see you all next class.